Hello everyone, this is Calculus 3, 2533 video lecture of section 12.3. In 12.1 and 2, we learned about double integral. Double integral over a rectangular domain was defined as limit of double Riemann sum. I from 1 through m, j from 1 through n, xij star, yij star, delta a, which is delta x, delta y. So, if f of xy is greater than or equal to 0, this is approximate, this double Riemann sum is a sum of the values of the rectangular column. And that will be approximating the volume of the region under the graph of y, z equals f of xy, z equals 0, xy plane, and these vertical walls above the rectangular domain R, right? Now, and also we learned that if it is in 12.2, we learned that this can be easily calculated if your rectangular domain is A to B, C to D, then that is actually iterative integral in both order. Okay, as long as f of xy is continuous, or in general, continuous except for the finite union of smooth curve. This is called Fubini's theorem. So this gives us a way to calculate double integral using our knowledge of definite integral you learned from calculus 1 and 2. All right? But still, it is only about rectangular domain. So a lot of times, the domain of the function is not just a rectangle. It could be general shapes. So this is the case we are going to consider today. So as usual, you might want to clean up the lecture note, which you can download from the course web page. All right, and then watch this video and write your own comments on the lecture notes. All right. So some of the stuff written on lecture notes I might not write here, but I might write something else here. Okay, so let's say your domain is regular domain D. This is the domain where your function f of xy is defined. Okay, so f of x, lowercase f of x, is defined on D. Now, here, this is the way we overcome this limit of this restriction on the general shape domain. We consider any rectangle R which encloses the domain D. We call it R. So let's say this is from A to B, C to D, right? Then we define so-called extension. Capital F of xy as f, same as f of xy. If your xy is over here inside the domain D, original domain D, then our capital F is same as lowercase f function. However, if your point is outside domain D but inside R, we define it as 0. Inside R but outside D. Okay? Then capital F is defined on the rectangle R. Okay? and it is continuous. So if you think about the graph, so it's hard to see. Okay. As you can see in the picture, if you're, this is a, so let's say these are the, shape of the z equals f of x, y. Then the rectangular domain is including like this. Okay? Then your graph of capital F of x, same as this surface, right? And then your capital F graph is, same as lowercase f. But then right outside this is collapse to the ground, right? So the graph of capital F is the graph of lowercase f is over here. This is domain, above the domain is. And suddenly it's a cliff, vertical cliff, down to zero, flat to the xy plane, because the value is 0, right? So certainly this will be, most in general, it will be discontinuous over a curve, boundary curve, right? As I said, Fubini theorem works not only for continuous function f, but a function which is continuous except for finite union of smooth curve. So assuming that boundary of domain D is smooth curve, this capital F is continuous. If f is, lowercase f is continuous, and continuous, and D, and capital F will be continuous, except for this boundary curve of D, right? The same is graph of lowercase f, and then vertical wall down to flat, 0. Okay? So, if you think about this double integral as a volume of this solid, right? This solid. Well, volume of this region is same as this because you flat to down to 0, right? So, when we define, then we define double integral of this lowercase f as double integral of this extension, we call it extension, on this enclosing rectangle. So we can use this definition of double integral over rectangle. All right? So we apply double integral over rectangle to this extension. But intuitively, the value must be same as this. If it were to measure the volume of the region bounded by the graph of function and xy plane, then the outside of original domain D is anyway, does not contribute to the volume because it's down to 0, the height is 0, flat. Okay? Now, then, okay, that's a nice definition. But our question is, how are we going to calculate this one practically? Linear of double Riemann sum is not a practical way of calculating the value. It's the introducing concept. It's not a practical method of evaluation. So we want to have something like this for this general case. All right? So before we do that, we have to consider two special types of domain. Okay? So-called type 1 and type 2. First of all, type 1 region is something like this. All right? This region can be described as this A to B So left hand side, x equals a, x equals b. Sometimes can be collapsed to one point, or it could be still line segment, vertical line segment. And this is upper function, y equals g2 of x. This one is y equals g1 of x. Okay? So for given x, think about these points. What kind of points are this? That would be y coordinate is g1 of x, g2 of x, right? So you can write this domain as set of all x, y such that this is domain D, right? X can be between A and D. For given x, the points in the domain D is those points for given x, the y coordinate will be between g1 of x to g2 of x. All right? As y goes, right, you're covering this one from here to here. That x can be here, here, starting from A all the way to B. When x is over here, that will be this. All right? By changing x values, you will cover every point, right? You'll cover every point. This is D. Okay? So if you can describe a domain as the region between two functions, g1 of x and g2 of x, between x equals a and b. If you can write your domain like that, we call it type 1 region. Okay? So in that case, now we define that double integral of f over this general type 1 domain is, now, we're going to consider any rectangle starting from A, B, like this. Okay? And for given x, this is our R can be anything enclosing original domain. All right? We chose exactly, yes, coinciding left hand side, right hand side, but top and bottom is enough cushion there. Then that is defined as domain of capital F of x. Right? Now, here, this one, you can write it from A to B, C to D, capital F of xy. Iterated integral from the result of section 4.2. Now, for given x, when y runs from C to D, this is C, this is D. Look at this. I can write this one inside one. Y runs from C to, what is it? This is g1 of x. And then from g1 of x to g2 of x. All right? And then g2 of x to d. Right? So for given x, this inside one's integral along this path, right? X is fixed. Y runs from here to here. I split into three regions. From C to g1 of x, g1 of x to g2 of x, and g2 of x to d. All right? This is this usual split of interval. dy of dx, right? So x is some fixed value. Y is the integrating variable. Look at this. From C to D, you're outside the domain D, inside R. So where your capital F is defined as 0, right? Over here is outside D, it is 0. Also, outside D, 0. So in the end, this is what you have. This is it. Okay? So if your domain is type 1, x runs from A to B, y runs from g1 of x to g2 of x, then the iterated integral of your domain integral of f of x over the domain D is exactly the way you described your domain as type 1. X runs from A to B. For given x, y runs from g1 of x to g2 of x. We integrated that. Okay? So that is the result of theorem. The top of page, second page, all right? If your domain is type 1 like this, okay? Likewise, type 2 is the region, just changing the roles of x and y. So it's like this. X equals h2 of y. X equals h1 of y. Did I use h? H. All right. And this is D. This is C to D. All right. So this is domain D. So you can write domain D here in set of points x and y, such that y runs from C to D, where given y, what is it? X coordinate runs h1 of y to h2 of y. Okay? So the roles of x and y are switched. Okay? Then you go through the exactly same argument. Then double integral of f of xy will be iterated integral. Y runs from C to D outside, and your x runs from h1 of y to h2 of y dy. Okay? So if you have, this is so-called type 2. If you have a type 2, which means you can describe your domain like this way. Y runs from where to where, and then for given y, x runs from some function of y to another function of y. A function whose graph is left-hand side curve, right-hand side curve. Okay? So, all right. So this is the generalized iterated integral from rectangular domain to general domain, either type 1 or type 2. Okay? So let's do some examples here. Example 1. What do you have? Example 1 is, okay, find the volume of the solid that lies under the plane and above the region, bounded by y equals x squared. Okay? All right. So is this the same thing? There's something different. Okay. So first of all, above the region domain is y equals x squared and y equals x. This is the domain D between y equals x, y equals x squared. Obviously, they don't intersect at 1. Okay? That's the domain. Okay? So your domain is, if you look at it, positive x, for your angle, positive x and positive y. This is xy plane. Y equals x squared, y equals x. So you have kind of like, first moon shape. Okay? And then above this and below what? Under the plane, z equals 2x plus y, isn't it? If you rewrite this equation, okay? Z equals 2x plus 2y it's a plane going rising. So if you have origin x, y axis, along the xz plane, it's just like z equals 2x. Along the y and z, it's like z equals y. So it's going up like this, right? Steeper here. Let's see. X, positive y, origin, z-axis, going like this. So our solid is here on the xy plane. You have this first moon shape, right? And above this, below this plane, rising plane. So you have to think about, this general cylinder whose cross-section shape is this region between y equals x squared, y equals x. And this top it off by this. So if you think about infinite cylinder, right? Infinite cylinder going up like this. And then it's cut with this plane, right? So your top of the cylinder is just slanted some planar region, and on this infinite cylinder, cut it this way. All right? So the volume of the solid is basically what? The height functions, double integral of the height function. This is your height function of the solid. All right? So x and y. Right? Going up. I don't know how to draw this. I don't know. I just described. It's so hard to draw. Anyway, let's cut it over here. All right? So your volume will be basically, this is your f of xy. And domain is, type 1. Because this is your g2 of x. This is your g1 of x. So your domain is x is between 0 and 1. Y runs from x squared to x. G1 of x, g2 of x. Okay. As I said before, I have to check the recording from time to time. Okay. So then the volume is double integral of this solid. That would be f of xy. That is 2x plus y dA. All right. Then this is using type 1, x runs from 0 to 1, right? X runs from 0 to 1. For given x, y runs from x squared to x dy. Okay? Now we do iterated integral. Okay? First of all, for y, now this is y integral. We consider 2x is just like a constant. So antiderivative of constant function is just that constant times y. Y runs from x squared to x. Y integral 1/2 of y squared. And here y equals x squared to y equals x. Okay? Then you get what? 2x times x minus x squared plus 1/2 x squared minus x squared squared. So x to the 4th. Okay? So in the end, you're going to get what? 2x squared minus 2x cubed, 1/2 of x squared minus 1/2 of x to the 4th. So you have a 5 over 2x squared minus 2x cubed. Right? And you just integrate this one with respect to x from 0 to 1. The rest of the calculation is so tedious and easy. Alright? You can look at the lecture notes. Alright? The most important thing is this setup. Alright? Setting up correctly. Using the fact that domain is type 1. Alright? Now, for this one, we can consider, so the first approach was considering, type 1. But, actually, we can consider this one as a type 2. Y runs from 0 to 1. Alright? For given y, you run from here to here. Then I have to write this one as x equals y. We have to solve it for x. This one, x equals positive square root of y. Alright? So this is so-called h2 of y. Y is h1 of y. So your domain D can be written. So this is, you see the second method? I'm just writing here rectangle. Y runs from 0 to 1. For given y, x runs from y to square root of y. You can write it that way. Then your integral can be set up. Y runs from 0 to 1. For given y, x runs from y to square root of y. Okay? Then you can do the usual. For with respect to x, this is x squared from y to square root of y plus y times x. See? Now, x equals y to x equals square root of y. Same thing here, x equals y to x equals this. Then this is y minus y squared here plus y times square root of y minus y. And these are, after distribute and combine like terms, you can finish the calculation easily. In the end, both of cases give you same number, 7 over 30. You can refer to the detailed calculation in the notes. The important thing is this 7. Okay? So, sometimes sometimes you can do domain is both type 1 and type 2. You can do both ways. Sometimes equally easily. Sometimes one domain can be considered as type 1 and type 2, but with type 1, easy. With type 2, very hard or impossible. Or the other way around. Okay? Sometimes, only one way can be done easily. The other way is hard or impossible. It's a case by case. All right? Now, example 2 is a hint for your homework. Okay, let's see. Your example 2 is number 30 on page 851. Hint only. Number 30. Bounded by the cylinder y squared plus z squared, okay, equals 4. And the plane y equals x, okay? So, y squared plus z squared equals 4. This is a circle on the xy plane, right? If you draw a region like this. Now, they say that find the volume of the region bounded by the cylinder, plane x equals 2y, x equals 0, z equals 0. Z equals 0 means this, right? XY plane. X equals 0 means YZ plane, right? YZ plane. And x equals 2y. X equals 0, z equals 0, and x equals 2y, or y equals 1/2 of x. So something like this. X equals 2y. Okay? Let's say this is x equals 2y. So this plane, and the bottom, and here. And then this is in YZ plane, there is a circle, right? There is a circle, but if you think about Y and Z and positive X, this is a circular cylinder, right? X can be anything. So if you think about X is coming out of the plane, Y and Z, circular plane, all right, X and Y, and there's a cut, and then YZ plane, right? So this is supposed to be a circle, right? Going here, but it is going like this. X equals 2y, y is 1/2 of x. So it is going like this. Yeah. All right. So think about this. It's a roll K. So when you roll K, semi upper half of roll K on the Y and X, Z, roll K. Roll K is going that way, and they cut it with this plane. Okay? So think about upper half of roll K is on the XY plane. Okay? Along the X direction. Along the X direction. X-axis. y-axis, z-axis, roll K, okay? Half cylinder, roll K, along the x-axis. And this is the plane x equals to y. You're cutting here and cutting here. X equals z, y z plane. XY plane, YZ plane, and this way. Upper is cylinder, circumscript. All right? So that's the case. You know, when you solve for this, z squared, z, 4 minus y squared is equals to the square root of 4 minus y squared or minus 4 minus y squared. But our case is because it's above the xy plane. So this is top surface, 4 minus y squared. And this is the bottom. All right? I'm going to call it D. All right? This one down to 2 here, at 2, right? And obviously this will be 4 in that case, but it's not there. Okay? So you can consider this solid as the region below this, domain of D here, this triangular domain, above this domain, below this graph. All right? That is the solid the problem is talking about. So your domain, if you redraw it in regular XY orientation, this is, x equals to y or y equals 1/2 of x, right? Same thing as y equals 1/2 of x. And y equals 2. Y equals 2. Y equals 1/2 of x. For given x, we're going this direction, isn't it? All right? So, you can write it as type 1, x runs from 0 to 4, and y runs from here to here. 2 is the upper function. You can write it that way. Or, this is x equals 0 versus x equals 2y. For a given y, you run from 0 to 2y. So you can write it as type 2. Y runs from 0 to 2. For given y, x runs from 0. Right? This is your h1 of y, h2 of y. This is type 2. Okay? So you can set up either way. Okay? And then your volume is double integral of 4 minus y squared dA. So if you analyze this iterate integral as a type 1, you're going to get 0 to 4, and y runs from x over 2 to 2 squared dy and dx, right? Now, when you try type 1, look at this. Antiderivative of square root of 4 minus y squared. It's not an easy one. If you have y here, then easy substitution, right? U equals 4 minus y squared. Then d with minus 2y dy equals du. So y dy will be minus 1/2 of du. And square root of u. Easy. But without y here, it is very hard. So Yeah, it is possible. If you do trigonometric substitution, you can do it, but it's going to be way more complicated. So before you try that route, why don't we try type 2 and see what happens. As a type 2, iterated integral 0 to y dy, x runs from 0 to 2y dx of this function. And then if you do that, what is it? With respect to x, this is constant. So this will be just this constant times x from 0 to 2y dy. That is just 2y, right? This 2y minus this 2y, 4 minus y squared dy. Okay. This is the easy substitution. U equals 4 minus y squared, right? So you can finish from there. So this problem illustrates the case. Even though the domain can be described easily as type 1 and type 2 both, sometimes one approach gives you very hard integral or impossible, but the other approach gives you very easy integral. So you have to be mindful of those possibilities. Okay? All right. Let me check the recording. All right. I think I have to split section 12.3 into two parts. Okay? So this is the end of the part 1 of section 12.3. All right? And then we'll finish section 12.3 in the part 2 video. Okay? Thank you, and see you next time.